Right now, something is touching you. You can't feel it. You can't see it. But it's there, passing through your skin, your walls, this room, the entire planet, without slowing down, without stopping. They do not slow down for you. They do not notice you. They have been traveling for 13.8 billion years, and you are simply the latest thing they have passed through on an infinite journey with no destination. Scientists call it the cosmic microwave background, the CMB, the oldest light in the observable universe, a remnant of the moment creation itself became possible. We call it remnant light. You've probably heard of the Big Bang, the moment, if we can even call it a moment, when everything began, when space itself expanded from a point of infinite density into the vast, cooling cosmos we now inhabit. But here is what most people do not know. The Big Bang did not produce light, not at first. For the first 380,000 years of the universe's existence, a span of time so incomprehensible that all of recorded human history would not register as a single heartbeat within it, the universe was dark. Not dark the way a room is dark, dark the way nothing is dark. A seething, opaque plasma of energy so dense that light could not travel more than a fraction of a millimeter before being absorbed and re-emitted, absorbed and re-emitted, trapped in an endless cycle, going nowhere. And then, something happened. The universe cooled to a precise temperature, 3,000 degrees Kelvin, to be exact, and in an instant that took approximately 100,000 years, electrons and protons combined to form the first hydrogen atoms. And for the first time in the history of everything, light was free. It streamed outward in every direction simultaneously. The entire universe lit up at once, a flash so total, so absolute, that nothing before it had ever seen light, and nothing after it would ever see anything older. That light is still traveling, right now. Through this room, through you. That is what this video is about. Not just what the CMB is, but what it means. What it tells us about the first moments of creation, about the structure of everything that exists, and about the almost unbearable strangeness of living in a universe old enough to be still glowing from its own birth. Let's go back to the beginning. The word before is a problem. When we ask what happened before the Big Bang, we are making an assumption so deeply embedded in how humans think that we rarely notice it. The assumption that time existed before the universe did. It didn't. Time, as best as we understand it, began with the universe, not inside the universe, not as a property the universe was born into. Time itself emerged with space, with energy, with everything. To ask what came before the Big Bang is a little like asking what is north of the North Pole. The question contains a direction that does not exist in the territory it is pointing at. So let us not ask what came before. Let us instead ask something we can actually answer. What was the universe like in its first moments? Imagine compressing everything that exists, every galaxy, every star, every planet,
every atom of everything that has ever existed or will ever exist, into a space smaller than a proton. Not a small room, not a pinhead, a proton. 100 million times smaller than the width of a human hair. Now imagine that object having a temperature. In the first fraction of a second after the Big Bang, we are talking about intervals so small they do not have names in ordinary language, time measured in units like the Planck time, which is 10 to the negative 43 seconds. The temperature of the universe was approximately 10 to the 32 degrees Kelvin. That number is so large it is almost meaningless to say it aloud, but let us try to feel its scale. The surface of our sun is approximately 5,800 degrees Kelvin. The core of our sun, the nuclear furnace at its heart, is approximately 15 million degrees Kelvin. The most powerful nuclear weapon ever detonated by human beings briefly achieved temperatures in the hundreds of millions of degrees Kelvin. The early universe was 100 trillion times hotter than that. At these temperatures, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, the weak nuclear force, were not four separate forces. They were one, a single unified force governing a universe so energetic that the distinction between matter and energy had no meaning. Particles flickered in and out of existence. Quarks and antiquarks annihilated each other and were reborn in the same instant. The universe was not a place, it was a process, a roiling, seething, expanding calculation working out what it was allowed to become. And then it began to cool. This is the part that matters. This is the story beneath the story. As the universe expanded, and it expanded extraordinarily fast in those first moments, a period we call cosmic inflation, its temperature fell. And as its temperature fell, the unified forces began to separate. Gravity peeled away first, then the strong nuclear force, then electromagnetism and the weak force split apart.
Each separation was a phase transition, like water freezing into ice, the universe crystallizing into new forms as it cooled, locking in the laws of physics as we now know them. By the time the universe was 1 second old, it had already lived several distinct lives. A second old. Let that sit for a moment. The entire history of the universe, from the initial singularity, through the unification of forces, through cosmic inflation, through the separation of the four fundamental forces, through the annihilation of almost all antimatter by matter, all of this happened before the universe was old enough to count to one. What remained 1 second in was a universe of protons, neutrons, electrons, photons, and neutrinos, all moving at extraordinary speeds, all colliding constantly, all trapped in a plasma so dense that light could not travel freely through it. The universe was opaque. Not dark in the way we will see later, bright, extraordinarily, violently bright, but impenetrable, like trying to see through a wall of fire. The light was there. It had always been there, born from the energy of creation itself, but it could not go anywhere. It was trapped. For now. 380,000 years. That is how long the universe waited in darkness. Not darkness the way we experience it, not the darkness of a power cut, or a moonless night, or a room with the curtains drawn. Those darknesses are temporary. They have edges. They end. This darkness had no edges. It was everywhere, all at once, in every direction, for every point in a universe that was itself expanding in every direction simultaneously. There was no outside to step into, no vantage point from which to observe it. There was simply the plasma, hot, dense, opaque, violent, and within it, light that could not escape. To understand what this period was like, you need to understand what plasma is. We are familiar with three states of matter: solid, liquid, gas. There is a fourth, plasma, which is what you get when a gas becomes so hot that its atoms are torn apart. The electrons, which normally orbit the nucleus of an atom, are stripped away by the sheer violence of the temperature and move freely through the gas as independent particles. The early universe was entirely plasma. Every single point in space was filled with a soup of free electrons, protons, neutrons, photons, and neutrinos, all colliding constantly, all interacting constantly, all preventing light from doing the one thing light does naturally: travel. A photon, a particle of light, generated in the heart of this plasma, would travel approximately 1 centimeter before colliding with a free electron and being scattered in a random direction. Then another centimeter, then another collision, another random direction, over and over and over again, in what physicists call a random walk, a path so chaotic, so directionless, that a photon generated in those first moments might travel for thousands of years and end up almost exactly where it started. The universe was a trap. And yet, and this is crucial, it was not silent. Because the plasma was not uniform, it had structure. Tiny quantum fluctuations from the very first moments of the Big Bang, variations in density so small they were essentially random, had been stretched by cosmic inflation into patterns that spanned the observable universe. Some regions were slightly denser than others, slightly hotter, slightly more compressed. Gravity pulled matter toward the denser regions. Radiation pressure pushed it outward again. Gravity compressing, radiation expanding, gravity compressing, radiation expanding, setting the plasma oscillating. Like a sound wave, like a note struck on a cosmic instrument so vast that its vibrations took hundreds of thousands of years to complete a single cycle. Cosmologists call these baryon acoustic oscillations. We might simply call them the sound of the early universe.
The universe was singing. Blind, trapped, opaque, but singing. And the song it sang in those 380,000 years would leave marks on everything that came after. The temperature fluctuations we see in the CMB today, those warm amber and cool blue variations in the oldest light, are the frozen record of those oscillations, a photograph of sound, a map of music made at the beginning of time. But that map could not be made yet. The light was still trapped. The plasma was still opaque. The universe was still waiting for the precise conditions that would set it free. It needed to cool to exactly 3,000 degrees Kelvin. It needed electrons and protons to slow down enough to find each other, to combine into the first neutral atoms in the history of existence. It needed a moment that cosmologists call recombination. It needed the universe to become transparent. That moment was coming.
There is a moment in the cooling of the universe that cosmologists call recombination. It is, in many ways, the most important moment in the history of everything. Not the Big Bang itself, that was the beginning, yes, but the beginning was chaos, pure, undifferentiated, unobservable chaos. Nothing that existed in those first fractions of a second has survived in any form we can directly detect. The physics of that moment remains, in important ways, beyond our reach. Recombination is different. Recombination left evidence. The word itself is slightly misleading. It implies that electrons and protons had been combined before and were now recombining, reuniting after a separation, but they had never been combined. This was the first time.
The name is a historical accident, a term coined before cosmologists fully understood what they were describing, and it stuck. What actually happened was this. For 380,000 years, the universe had been cooling, expanding, thinning. The temperature that had begun at 10 to the power of 32 degrees Kelvin in the first instant had been falling steadily, not slowly, but steadily, as the cosmos grew larger and its energy spread across an ever-increasing volume of space. By 380,000 years after the Big Bang, the temperature had fallen to approximately 3,000 degrees Kelvin. At that temperature, something became possible that had never been possible before. Electrons slowed down enough to be captured by protons. Not all at once, not in a single instant. Over a period of roughly 100,000 years, which sounds long, but remember we are measuring against a universe that had already existed for 380,000 years. Electrons and protons across the entire observable universe began finding each other, combining, forming the first neutral hydrogen atoms in the history of existence. And as each atom formed, something extraordinary happened. The free electrons, the particles that had been scattering light, trapping photons in their endless random walk, disappeared, not destroyed, simply bound, incorporated into atoms, no longer free to interrupt the journey of light. And the universe, for the first time, became transparent. Imagine it. For 380,000 years, every photon in the universe had been trapped, scattered, redirected, absorbed and re-emitted, going nowhere. And then, over the course of 100,000 years, the trap dissolved. The walls came down. The plasma cleared like fog burning off on a cold morning. And suddenly, in every direction, simultaneously, across the entire observable universe, light was free. It streamed outward, in every direction at once, at the speed of light. And it has been traveling ever since.
That light, the light released at the moment of recombination, is what we call the cosmic microwave background. It is not light from stars. It is not light from galaxies. It predates stars. It predates galaxies. It predates every structure in the universe except the large-scale patterns seeded by those earliest quantum fluctuations. It is the light of the universe itself, released at the first moment the universe was capable of releasing it. And here is what I want you to hold in your mind.
That light did not travel to a destination. There was no destination. The universe was not expanding into empty space. It was space itself that was expanding, carrying everything with it. So the light released at recombination did not stream outward from a central point. It streamed outward from every point simultaneously. Every point in the universe was the origin, including the point in space that our planet would eventually occupy 9 billion years later, which means that the light released at recombination, the oldest light in existence, has been converging on Earth from every direction since long before the Earth existed, streaming toward us across 13.8 billion years, passing through clouds of hydrogen that would become galaxies, through the births and deaths of generations of stars, through the formation of our solar system, the cooling of our planet, the emergence of life, and the entire span of human history, and arriving right now, here, in this room, passing through you. This is remnant light. This is what we are named after.
In 1964, two radio astronomers at Bell Telephone Laboratories in New Jersey were trying to eliminate a noise. Their names were Arno Penzias and Robert Wilson. They were not looking for the oldest light in the universe. They were not trying to confirm or refute any cosmological theory. They were engineers, essentially, practical men with a practical problem. They had been assigned to a large horn-shaped antenna in Holmdel, New Jersey, originally built to communicate with early satellites, and they were attempting to use it for radio astronomy. But there was a noise. Not a loud noise, not an obvious noise, a persistent, low-level microwave hiss that appeared in their data regardless of where they pointed the antenna. North, south, east, west, up, down, the signal was everywhere. It did not vary with the time of day. It did not vary with the season. It was isotropic, meaning it came equally from every direction in the sky simultaneously. Penzias and Wilson were methodical men. They went through every possible explanation. Interference from nearby New York City. Eliminated. The signal was too uniform, too directionless to come from a terrestrial source. Interference from military radar. Eliminated. Same reasoning. A technical fault in the antenna itself. Investigated exhaustively. Found nothing. And then they found something inside the antenna. Pigeons. A pair of pigeons had nested inside the horn of the antenna, and as pigeons do, had coated the interior with what Penzias and Wilson described in their notes with admirable scientific restraint as a white dielectric material. They removed the pigeons. They cleaned the antenna. They tried relocating the pigeons to a facility some distance away. The pigeons returned. They were, in the end, dealt with more permanently. The hiss remained. What Penzias and Wilson did not know, what they had no reason to know, was that approximately 60 kilometers away at Princeton University, a team of physicists led by Robert Dike was actively searching for exactly the signal they were trying to eliminate. Dike's team had been working from the theoretical predictions of George Gamow, Ralph Alpher, and Robert Herman, who in the late 1940s had proposed that if the Big Bang had actually occurred, it should have left behind a detectable afterglow, a bath of radiation filling the entire universe, cooled by expansion to just a few degrees above absolute zero. Dike's team was building a detector to find it. They were, as Dike himself would later put it with considerable understatement, scooped.
A mutual contact connected the two groups. Penzias called Dyke. Dyke listened to the description of the signal. He put down the phone, turned to his colleagues. "Boys, we've been beaten."
What Penzias and Wilson had found, the noise they had spent months trying to eliminate, the hiss they had blamed on pigeons, was the cosmic microwave background, the oldest light in the observable universe. The remnant of recombination, stretched by 13.8 billion years of cosmic expansion from visible light into microwave radiation, cooled to a temperature of approximately 2.725 degrees Kelvin, just barely above absolute zero. They had been pointing their antenna at the afterglow of creation and trying to make it go away. In 1978, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics for their discovery. Robert Deke, whose theoretical framework had predicted exactly what they found, was not included. The Nobel Committee does not award prizes for predictions, only for discoveries. It is one of the more quietly painful ironies in the history of science. But here is what strikes me most about this story. It simply waited, as it had always waited, as it will continue to wait long after every instrument we have ever built has turned to dust. Patient beyond all human understanding. Arriving.
Finding the cosmic microwave background was one thing. Reading it was another. Penzias and Wilson had confirmed its existence. They had measured its temperature with remarkable precision. They had established, beyond any serious scientific doubt, that the universe had begun in a state of extraordinary heat and density and had been expanding and cooling ever since. But the CMB they detected was smooth, perfectly, almost suspiciously smooth. The same temperature in every direction to a precision of 1 part in 100,000. And that smoothness was, in its own way, a problem. Because the universe we live in is not smooth. Look up on a clear night and you see stars, not distributed evenly across the sky, but clustered, gathered into galaxies. Galaxies gathered into clusters. Clusters gathered into superclusters. Vast cosmic structures hundreds of millions of light years across, separated by equally vast voids where almost nothing exists. The universe has texture, it has grain, it has structure on every scale we have been able to measure. And structure requires seeds. Something in the early universe must have been slightly uneven, slightly denser here, slightly less dense there, to give gravity something to work with. Without those initial variations, matter would have distributed itself perfectly uniformly across the expanding cosmos, and gravity would have had nothing to pull together, and galaxies would never have formed, and stars would never have ignited, and planets would never have coalesced, and we would not be here to ask any of these questions. The seeds of everything that exists had to be somewhere in the CMB, but Penzias and Wilson's instruments were not sensitive enough to find them.
In 1989, NASA launched a satellite called COBE, the Cosmic Background Explorer. Its mission was to map the CMB with a precision that ground-based instruments could never achieve, free from the interference of Earth's atmosphere, scanning the entire sky systematically over the course of 4 years. In 1992, the COB team announced their results. The CMB was not perfectly smooth. There were variations, tiny fluctuations in temperature measured in millions of a degree, scattered across the sky in a pattern that was neither random nor regular, warmer regions and cooler regions, denser and less dense. The seeds of all cosmic structure, frozen into the oldest light in the universe, preserved across 13.8 billion years of expansion with extraordinary fidelity. The lead scientist on the COB project, George Smoot, described the discovery with a phrase that has stayed with cosmology ever since. "If you're religious," he said, "it's like seeing the face of God." COB gave us the first map, but it was a blurry map, low resolution, capable of showing only the broadest features of the CMB's structure. Two subsequent missions sharpened the picture considerably. WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001 and produced a map of such precision that cosmologists could use it to measure the age of the universe, its geometry, its composition, and the rate of its expansion, all from a single image of ancient light.
And then Planck, a European Space Agency mission launched in 2009, produced the most detailed map of the CMB ever made. A portrait of the universe as it was 380,000 years after the Big Bang, rendered in such exquisite detail that the fluctuations in temperature could be traced to individual quantum events in the first moments of creation. What these maps tell us is almost overwhelming in its scope. The universe is 13.8 billion years old, measured from the CMB with a precision of less than 1%. Its geometry is flat, meaning parallel lines stay parallel across the observable universe. Space does not curve back on itself. It is composed of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy, and the CMB maps were instrumental in establishing each of those figures. And the fluctuations, those tiny temperature variations that COB first detected, match the predictions of inflation with a precision that remains one of the most stunning confirmations in the history of science. The universe left us a map, written in light, addressed to anyone patient enough to learn to read it. We are only just beginning.
WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001 and produced a map of such precision that cosmologists could use it to measure the age of the universe, its geometry, its composition, and the rate of its expansion, all from a single image of ancient light. And then Planck, a European Space Agency mission launched in 2009, produced the most detailed map of the CMB ever made. A portrait of the universe as it was 380,000 years after the Big Bang, rendered in such exquisite detail that the fluctuations in temperature could be traced to individual quantum events in the first moments of creation. What these maps tell us is almost overwhelming in its scope. The universe is 13.8 billion years old, measured from the CMB with a precision of less than 1%. Its geometry is flat, meaning parallel lines stay parallel across the observable universe. Space does not curve back on itself. It is composed of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy,
and the CMB maps were instrumental in establishing each of those figures. And the fluctuations, those tiny temperature variations that COBE first detected, match the predictions of inflation with a precision that remains one of the most stunning confirmations in the history of science. The universe left us a map, written in light, addressed to anyone patient enough to learn to read it. We are only just beginning.
Let us come back to this room, to you, sitting or lying wherever you are right now, listening to this. The light we have been talking about, the oldest light in the observable universe, released 380,000 years after the Big Bang, traveling for 13.8 billion years without stopping, is here, right now, in this room, passing through the walls, through the ceiling, through your body, through the floor, continuing its journey in every direction simultaneously, indifferent to everything it passes through. You are at this exact moment bathed in the afterglow of creation. But there is something more than that. Something that took me a long time to fully feel the weight of. The temperature fluctuations in the CMB, those tiny variations in density that COBE and WAMAP and Planck mapped with such precision, are not just the seeds of galaxies in the abstract. They are the seeds of specific galaxies, specific clusters, specific filaments of cosmic structure, including the filament that contains our galaxy, including the galaxy that contains our star, including the star that formed our planet, including the planet that produced, after 4 billion years of chemistry and biology and catastrophe and improbable fortune, us. The pattern written in the CMB is not just a map of the universe in general. It is the map that led step by inexorable step to this specific moment. We are not observers of the CMB. We are its consequence. Every atom in your body was forged in the heart of a star that formed from clouds of hydrogen that collapsed along the filaments of structure seeded by those temperature fluctuations. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all of it traces back through generations of stars, through billions of years of cosmic chemistry, to the patterns frozen in the oldest light in existence. The CMB did not just precede us, it made us. There is a concept in cosmology called the last scattering surface. It is the name given to the spherical shell of space from which the CMB photons we detect today were last scattered before traveling freely to reach us. Every photon in the CMB that has ever been detected on Earth originated on that surface. A sphere approximately 46 billion light-years away in every direction, representing the furthest back in time we can ever directly observe. It is the edge of the observable universe. It is the oldest thing we can see. And it is arriving here at this point in space right now from every direction simultaneously, as if the universe arranged itself specifically so that this place, this planet,
This moment would be at the center of the oldest light in existence. Every point in the universe is at that center. Every point receives the signal equally. But you are here, at this point, receiving it. That is not nothing.
The universe is 13.8 billion years old. It has been expanding and cooling since a moment we cannot see beyond. It has formed 100 billion galaxies, each containing hundreds of billions of stars, across a volume of space so vast that the numbers lose their meaning long before they approach its edges. And somewhere in that vastness, on a small planet orbiting an unremarkable star in the outer arm of one ordinary galaxy among billions, something happened that may be unique in all of that immensity. The universe became aware of itself, began to ask questions about its own nature, built instruments to detect its own oldest light, learned to read the map it left itself at the moment of its own creation. We are how the universe knows it exists. Ancient signals finally arriving. If this is the kind of question you want to sit with, there are more coming. The next signal arrives in 10 days. What does it mean to you that this light is passing through you right now? Leave it below. I read everything.